Well, welcome back to our class on college physics. We're continuing on and turns out that initially I apologize for early lectures that I had mislabeled this. So we're finishing up now the mechanics section, and you can see with 9 topics, there's a lot of material that'll be part of this one thing, different types of motion, different types of ways of looking at it, whether it be linear or rotational motion, energy. And now we're going to be looking in this lecture, be looking at fluids and solids. And so we'll just get into this right away here. And so you can see in the picture an iceberg. And so we're seeing an interesting display of both liquid and solids, all of the same substance. And interesting how the characteristics of water is very unique, that when it is solid, it actually is less dense, and so it actually floats. And that is a very intriguing and important characteristic, one of a huge number of characteristics that are important, the way that things are organized. So as usual, we have some reading questions we'll go over quickly. We'll go over the basic concepts of the material. We'll intersperse that with some questions that we'll think about, and then we'll have a summary. So in terms of the reading, so this first one is to describe the relationship between the stress and strain for a cube of Jello when it jiggles from side to side. Which of the following would we use? You might want to think about that a little bit here, but the answer is you want to be looking at the shear modulus. And if you go through the reading, I think you'll get a chance to get some more insight into that. Which of the following cases would the maximum, quote, constant pressure from the floor on a person be the least? And so the answer is when the person is lying down on the floor. So you can think about that a little bit as where do they have a constant pressure? It's not just part of their body, but the maximum part of their body when they're lying down. 2 pipes are smoothly connected together without leaks. One has a diameter of 3 centimeters and the other has a diameter of 5 centimeters. Water flows through the pipes. In which pipe is the volume flow rate the greatest? And the answer is in neither. The flow rate is the same in both pipes. So, and for this one, a block of steel is found on a ship sunken in 5,000 meters of water where the pressures are about 500 times that of Earth at sea level. To know its dimension at sea level, which relationship between stress and strain for the metal would you need to know? The answer is the bulk modulus. So we're talking about solids and liquids here. So these are things that you'll get a chance to understand a little bit better as a result of this chapter. So the pressure at the bottom of a glass of fresh water, where P is 1,000 kilograms per meter cubed, is P. The water is poured out and is replaced with seawater. The new pressure at the bottom of the glass is greater than P. So you can see that there is a difference between fresh water and salt water. And so we'll get some more insight as we go through the material in this chapter. So there are 4 known states of matter: solids, liquids, gases, and plasmas. For the most part, we are familiar with the first 3, but plasmas, which are systems of charged particles interacting electromagnetically, are in fact the most common. An understanding of the fundamental properties of these different states of matter is important in all the sciences, in engineering and in medicine. Force puts stresses on solids, and stresses can strain, deform, and break those solids, whether they are steel beams or bones. Fluids under pressure can perform work or carry nutrients in essential solutions, like the blood flowing through our arteries and veins. Flowing gases cause pressure differences that can lift a massive cargo plane or the roof off a house in a hurricane. High temperature plasmas created in fusion reactors may someday allow humans to harness the energy source of the sun. So in this chapter, we will introduce get an introduction to the basic properties of the three most common states of matter here on Earth. We'll also look at the phenomena such as surface tension, viscosity, osmosis, and diffusion. So actually a fair amount of material. So in this figure, we have a model of a portion of a solid. The atoms, which are displayed here as spheres, are imaged as being attached to each other with springs, which represent the elastic nature of the interatomic forces. A solid consists of trillions of segments like this, with springs connecting all of them. So we know from our everyday experience that solids has a definite volume and shape. Think of a brick, for example, its size and shape is constant. A liquid, on the other hand, has a definite volume, but no definite shape. Imagine filling the tank of a lawnmower. The gasoline changes its shape from that of the original container to that of the tank on the mower, but the original volume is unchanged. Gas doesn't have a definite volume or a definite shape. It can flow, so gases and liquids share many properties. All matter consists of atoms or molecules. In a solid, the atoms are held together primarily by electric forces, and each atom is located at a specific position with respect to the other atoms in the solid. The figure shows a model of a portion of a solid. Atoms in solids are able to vibrate about their position, similar to the balls attached to the springs in the model shown. At low temperature, the vibrating motion is slight, and the atoms can be considered essentially fixed. So in this figure, on the left, we show crystals of natural quartz, silicon oxide, one of the most common materials on Earth. Quartz crystals are used to make special lenses and prisms and are employed in certain electronic applications. And on the right, we have a sodium chloride structure with the sodium shown in one way and gray, if you will, and the chloride is in green at alternate quarters of the cube. So there are two classifications of solids, crystalline or amorphous. In a crystalline solid, such as the quartz shown in the photo, the atoms have an ordered structure. Sodium chloride, or common table salt, is another example of crystalline solid. The figure on the right shows the sodium chloride atoms, which occupy alternate quarters of a cube. In this figure, sodium atoms are represented by the large green spheres, while the chlorine atoms are by the smaller brown or gray, however you want to maybe think about it, spheres. So here's an amorphous solid example. The atoms are arranged randomly. So in an amorphous solid such as glass, the atoms are arranged almost randomly, as you can see in the figure. Here we're trying to show erratic motion of a molecule in a liquid. Liquids exist at a higher temperature than the solid state of that material. The intermolecular forces in a liquid aren't strong enough to keep the molecules in fixed positions, and they wander through the liquid randomly, as you can see in the figure. Solids and liquids both resist compression due to their strong repulsive atomic forces. In gases, on the other hand, molecules are in constant random motion and exert only weak forces on each other. The average distance between the molecules of a gas is quite large compared with the size of the molecules. Occasionally, the molecules collide with each other, but most of the time they move as nearly free, non-interacting particles. For this reason, gases can be easily compressed. So now we're looking up at the heavens here, and we're seeing what's something called an accretion disk. And so when a gas is heated to high temperatures, many of the electrons surrounding each atom are freed from the nucleus, resulting in a collection of free electrically charged particles, negatively charged electrons, and positively charged ions. The state with equal amounts of positive and negative charges is called a plasma. In a plasma, the long-range electric and magnetic forces mean that the charged particles interact with each other. Plasmas can be found inside stars and an accretion disk around black holes, as shown in the figure. Plasmas are much more common than solids, liquids, or gases because there are more stars around than any other form of celestial matter. So it's maybe not things that we would see coming here and going there, driving in our car, being at home. But if you think in terms of space, there's a lot more plasmas is what they're trying to get at. So say you had two equal masses of aluminum and gold. One thing you would notice immediately is that the aluminum takes up over 7 times much space as the gold. The way we quantify this difference is by looking at the concept of density. The density of an object having uniform compositions is its mass divided by its volume. So we're getting a table here to help us get some perspective on this. So the table shows the densities of some substances. The densities of most liquids and solids vary slightly from changes in temperature and pressure. For gases, though, the densities vary a lot when the temperature and or pressure is changed. Under normal conditions, the densities of solids and liquids are about 1,000 times greater than the densities of gases. This difference implies that the average spacing between molecules in a gas under such conditions is about 10 times greater than in a solid or liquid. So we'll introduce another term here. The specific gravity of a substance is a ratio of the density to the density of water at 4 degrees Celsius, which is 1,000 kilograms per meter cubed. So let's make some quick calculations. Write your list and we can think about this here. So suppose you have 1 cubic meter of gold, 2 cubic meters of silver, and 6 cubic meters of aluminum. We want to rank them by mass from smallest to largest. And so the answer is aluminum, and then gold, and then silver. Now let's think about density and pressure. So in the figure we have, in A, we have the force exerted by a fluid on the surface of a submerged object. And B, we have a simple device for measuring pressure in a liquid. The force exerted by a fluid on an object is always perpendicular to the surface of the object, as can be seen in the figure on the left. The pressure of a specific point in a fluid can be measured with the device pictured in the figure on the right. This is an evacuated cylinder and closing a light piston connected to a spring. Spring has been previously calibrated with known weights. When the device is submerged in a liquid, the fluid presses down on the top of the piston and compresses the spring until the inward force exerted by the fluid is balanced by the outward force exerted by the spring. So let F be the magnitude of the force on the piston, A, the area of the top surface of the piston. Notice that the force that compresses the spring is spread out over the entire area. This gives us a way to define pressure. If F is the magnitude of a force exerted perpendicular to a given surface of area A, then the average pressure is the force divided by the area. The English customary unit for pressure is the pound per square inch. Atmospheric pressure at sea level is 14.7 pounds per square inch, which is in SI units is 1.01 times 10 to the 5. And so that's the SI measurement for that. So here we're seeing an interesting example of snowshoes, and snowshoes prevent a person from sinking into the soft snow because the force in the snow is spread over a larger area, reducing the pressure of the snow surface. You maybe have had that experience of walking in the snow. If you didn't have these things, your feet would cave into the snow depending on the density of the snow that you're walking on. The effect of a given force depends on the area. Consider a 900 Newton man standing on a vinyl covered floor in regular street shoes. No harm comes to the floor, but imagine he changed into golf shoes. The metal cleats on the soles can do considerable damage on the floor. With the cleats, the same force is concentrated into a smaller area, which increases the pressure and can exceed the ultimate strength of the floor material, resulting in damage. So the snowshoes use the same principle. The snow exerts an upward force on the shoes to support the person's weight. According to Newton's third law, the upward force is accompanied by a downward force exerted by the shoes on the snow. If the person is wearing snowshoes, that force is distributed over the very large area of each snowshoe so that the pressure at any given point is relatively low and the person doesn't penetrate very deep into the snow. Here we have in a static fluid, all points at the same depth are at the same pressure, so the force F1 must be equal to the force F2. Consider a fluid in a container such as water in a bucket. When a fluid is at rest in the container, all portions of the fluid must be in static equilibrium. It means at rest with respect to the observer. Also, all points at the same depth must be the same pressure. Imagine this were not the case, that the fluid would flow from the high pressure region to the lower pressure region. For example, consider the small block of fluid shown in the figure. Note that this fluid is not separate from the rest of the fluid. This is just to indicate a particular volume of the fluid. If the pressure were greater on the left side of the block than on the right, F1 would be greater than F2 and the block would accelerate to the right and wouldn't be in equilibrium. So let's consider this figure. Because the volume of the shaded fluid isn't sinking or rising, the net force must be equal to 0. So let's take a look at this figure. Again, the dark region in the middle of the fluid is actually just a defined region within the fluid. The region has cross-sectional area A and extends from position Y1 to position Y2 below the surface of the liquid. 3 external forces act on this volume of fluid: the force of gravity, mg, the upward force, P2A, and exerted by the liquid below it, and the downward force, P1A, exerted by the liquid above it. Because the given volume of liquid is in equilibrium, these forces must add to 0, as shown in the equation. So we can rewrite this equation in terms of density. Putting these two equations together and rearranging, we get the result here. Notice that y1 minus y2 is positive because y2 is less than y1. The force P2A is greater than the force P1A by exactly the weight of water between the 2 points. This is the same principle experienced by the person at the bottom of a pileup in football or rugby. So maybe that might give you a perspective of something that might be a little bit more familiar. So in the figure, we have the photograph illustrates the fact that the pressure in a liquid is the same at all points, lying at the same elevation. Note that the shape of the vessel does not affect the pressure. Atmospheric pressure is also caused by a pileup of fluid. In this case, the fluid is the gas of the atmosphere. The weight of the air from sea level to the edge of space results in the atmospheric pressure of 1.01 times 10 to the 5th at sea level. We see this we can use this to find the pressure P at any depth below the surface of the water, as shown in the figure. According to this equation, the pressure P at a depth h below the surface of a liquid open to the atmosphere is greater than atmospheric pressure by the amount PGH, nu GH. This equation is often called the equation of hydrostatic equilibrium. Also, the pressure isn't affected by the shape of the vessel, as you can see in the photo. So let's take a question here. The pressure at the bottom of the glass filled with water is P. The water is poured out and the glass is filled with ethyl alcohol. The pressure at the bottom of the alcohol is now, and the answer is smaller than P. So at a fixed depth, the pressure in a liquid is directly proportional to the density of the fluid. Since ethyl alcohol is less dense than water, the pressure is smaller than P when the glass is filled with alcohol. So once again, you just have to be looking at these densities here and compare them, and you see that alcohol is less dense. So in this figure, in a hydraulic press, an increase of pressure in the smaller area A1 is transmitted to the larger area A2 because force equals pressure times area. The force F2 is larger than F1 by a factor of A2 over A1. Because the pressure in a fluid depends on depth and on the value of P0, any increase in pressure at the surface must be transmitted to every other point in the fluid. This phenomenon was first recognized by the French scientist Pascal, who lived from 1623 to 1662, and is called Pascal's principle. Pascal's principle states that a change in pressure applied to an enclosed fluid is transmitted undiminished to every point of the fluid and to the walls of the container. An important application of Pascal's principle is the hydraulic press, as shown in the figure and in the photo. Look at the schematic on the left. A downward force F1 is applied to a smaller piston of area A1. The pressure is transmitted through a fluid to a larger piston of area A2. As the pistons move and the fluids in the left and the right cylinders change their relative heights, there are slight differences in the pressures at the input and output pistons. Let's neglect these small differences, which means we can say the fluid pressure on each of the pistons may be taken to be the same, P1 equals P2. From the definition of pressure, we see that the force divided by the area for each side is also equal. So F2 is greater than F1 by a factor of A2 divided by A1. That's how a large load, such as a car, can be moved on the large piston by a much smaller force on the smaller piston. Hydraulic brakes, car lifts, hydraulic jacks, forklifts, and other machines make use of this principle. So once again, we're seeing some interesting physical phenomena that maybe might not intuitively be obvious unless you think about it, and hopefully this class will help you to be able to use those in the future. So here we have a device for measuring pressure, an open tube manometer, and the figure shows a simple device for measuring pressure called the open tube manometer. One end of the U-shaped tube containing a liquid is open to the atmosphere, and the other end is connected to a system of unknown pressure. Unknown pressure P. The pressure at point B equals P0 plus nu GH, where nu is the density of the fluid. The pressure at B, however, equals the pressure at A, which is also the unknown pressure P. We can conclude that P equals P0 plus nu GH. Pressure P is called the absolute pressure, and P minus P0 is called the gauge pressure. If P in the system is greater than the atmospheric pressure, H is positive. If P is less than the atmospheric pressure, which implies a partial vacuum, H is negative, meaning that the right-hand column is lower than the left-hand column. So in this figure, we have a device for measuring pressure, different one. This is called a mercury barometer. Here, we see another instrument used to measure pressure called a barometer. The barometer was invented by Torricelli, who lived from 1608 to 1647. A long tube enclosed at one end is filled with mercury and then inverted into a dish of mercury. The closed end of the tube is nearly a vacuum, so its pressure can be taken to be zero. It follows that P0 equals nu GH, where nu is the density of the mercury and H is the height of the mercury column. Note that the barometer measures the pressure of the atmosphere, whereas the manometer measures the pressure in a closed fluid. 1 atmosphere of pressure is defined to be a pressure equal to a column of mercury that is exactly 0.76 meters in length at 0 degrees Celsius, with G defined as shown on the slide. At this temperature, mercury has a density of 13.595 times 10 to the third kilograms per meter cubed. From this data, we can calculate our value for atmospheric pressure. It is interesting to note that the force on the atmosphere on our bodies assumes a body area of 2,000 square inches is extremely large on the order of 30,000 pounds. If it were not for the fluids permeating our tissues and body cavities, our bodies would collapse. The fluid provides equal and opposite forces. In the upper atmosphere or in space, sudden decomposition can lead to serious injury and death. Air retained in the lungs can damage the tiny alveolar sacs, and intestinal gas can even rupture internal organs. So here's another question. Several common barometers are built using a variety of fluids. For which fluid will the column of fluid in the barometer be the highest? And the answer is ethyl alcohol. And you may want to be thinking about this. For a fixed pressure, the height of the fluid in a barometer is inversely proportional to the density of the fluid. Of all these fluids listed in the selection, ethyl alcohol is the least dense. So that's the reason why that would be the answer. So why don't we'll think about here. And so we have this density of some common substances, and for a fixed pressure, the height of the fluid in a barometer is inversely proportional to the density of the fluid. The fluid, since it's here, the selection ethyl alcohol is the least dense. And so hopefully this table will maybe be something you can refer to later and helps us to answer this question in more detail. Okay, for those of you who are on the health side, this may be a familiar device. And so here we have a way of measuring blood pressure. So blood pressure is often measured using a specialized manometer called a, I'm not exactly sure how to pronounce this. So Sergio manometer, as illustrated in the figure, a rubber bubble forces air into a cuff wrapped tightly around the upper arm and simultaneously into a manometer. Pressure in the cuff is increased until the flow of blood through the brachial artery in the arm is stopped. Valve on the bulb is then open, and the measure listens with a stethoscope to the artery at the point just below the cuff. When the pressure in the cuff and brachial artery is just below the maximum value produced by the heart, the systolic pressure of the artery opens momentarily on each beat of the heart. At this point, the velocity of the blood is high and turbulent, and the flow is noisy and can be heard with a stethoscope. The manometer is calibrated to read the pressure in millimeters of mercury, and the valve obtained is about 120 millimeters for a normal heart. As the pressure in the cuff is lowered further, intermittent sounds are still heard until the pressure falls just below the minimum heart pressure, the diastolic pressure. At this point, continuous sound are heard in the normal heart. This transition occurs at about 80 millimeters of mercury. Blood pressure readings are usually expressed as a ratio of the systolic pressure to the diastolic pressure, which is 120/80 for a healthy heart. So hopefully this might give you some perspective of an instrument that some of you were fairly familiar with. So for blood pressure is normally measured with a cuff of this manometer around the arm. Suppose that the blood pressure is measured with a cuff around the calf of the leg of a standing person. The reading of the blood pressure will be, and the answer is greater than that for the arm. And so the reason would be the blood pressure measured at the calf would be larger than measured at the arm if we imagine the vascular system of the body to be vessels containing a liquid of blood. The pressure in the liquid will increase with depth. The blood at the calf is deeper in the liquid than in the arm and is at higher pressure. Blood pressures are normally taken at the arm because this is approximately the same height as a heart. If blood pressure at the calf were used as a standard adjustment would need to be made for the height of the person, the blood pressure would be different if the person were lying down. So here we have a figure with the arrows indicate forces on the sphere of fluid due to pressure, larger on the underside because pressure increases with depth. And so we're looking at buoyant buoyant forces and Archimedes' principle. So Archimedes' principle says that any object completely or partially submerged in a fluid is buoyant up by the force with magnitudes equal to the weight of the liquid displaced by the object. You have all probably experienced Archimedes' principle. It's relatively easy, for example, to lift someone if you're both standing in the swimming pool, but lifting that same person on dry land may be a difficult task. Water provides partial support to any objects placed in it, and the upward force is called the buoyant force. The physical cause of the buoyant force is the pressure difference between the upper and lower sides of the object. Let's say, take a look at the figure here, that the fluid indicated by the dark color is pressured on all sides by the surrounding fluid. The arrows indicate the forces arise from the pressure. Remember that pressure increases with depth, so the arrows on the bottom are larger than those on top. Adding them all up, the horizontal component cancel, but there is a net force upward. This force, due to difference in pressure, is the buoyant force. Since the sphere of water neither rises nor falls, the vector sum of the buoyant force and the force of gravity on the sphere of fluid must be zero, and it follows that B equals mg, where m is the mass of the fluid. Therefore, the buoyant force is equal to the magnitude to the weight of the displaced fluid. So the buoyant force, which is caused by the surrounding fluid, is the same on any object of the ball, or the same ball, including the cannonball. And so now we can imagine replacing the sphere of water with a cannonball that changes only the mass on which the pressure acts. So the buoyant force is the same, B equals mg, where m is the mass of the displaced fluid, not the mass of the cannonball. The force of gravity on the heavier ball is greater than it was in the fluid, so the cannonball sinks. We can also obtain Archimedes' principle using this figure. The horizontal forces from the pressure cancel, but at the vertical direction, P2A acts upwardly on the bottom of the block of fluid, and P1A and the gravity force on the fluid mg act downward. The buoyant force is a result of the difference in the pressure and is equal in magnitude to the weight of the displaced fluid. This buoyant force is the same no matter what material is occupying the volume, because it is due to the surrounding fluid. Using the definition of density, we can rewrite our equation. Here, nu fluid is the density of the fluid, and V fluid is the volume of the displaced fluid. The result applies equally to all shapes because any irregular shape can be approximated by a large number of infinitesimal cubes. So now we're looking at a case with a totally submerged object. And so a totally submerged object that is less dense than the fluid is submerged and acting upon a net force upward. And then we also have a case for a totally submerged object that is denser than fluid. So two's particular case here. So let's see what's happening when an object is totally submerged in a dense fluid of density nu fluid. The upward buoyancy force act on the object has a magnitude is given in the first equation, where V object is the volume of the object if the object has density nu object. The downward gravitational force W acting on the object has a magnitude given by the second equation shown. Now we can write an equation for the net force. This equation tells us that the density of the object is less than the density of the fluid. The net force exerted on the object is positive, that is upward, and the object's acceleration accelerates upward, as in the left-hand figure. If the density of the object is greater than the density of the fluid, as in the right-hand figure, the net force is negative and the object accelerates downward. So here in the figure, we have an object floating on the surface of a fluid is acting upon by two forces, the gravitational force F sub G and the buoyant force is B. Now consider a partially submerged object in static equilibrium floating in a fluid as shown in the figure. In this case, the upward buoyancy force is balanced by the downward force of the gravity acting on the object. If V fluid is the volume of the fluid displaced by the object, which corresponds to the volume of the part of the object beneath the fluid level, then the magnitude of the buoyant force is given by the first equation shown. from the weight of the object and the relationship between weight and the buoyancy force, we can derive a relationship between the densities and volumes of the fluid and object. Let's think about some real world examples of this. Under normal circumstances, the average density of a fish is slightly greater than the density of water. So a fish would sink if it didn't have a mechanism for adjusting its density. Fish changes the size of an internal swim bladder so it can contain neutral buoyancy as it swims to various depths. The human brain is immersed in a fluid called the cerebral spinal fluid, which has a density slightly less than the average density of the brain. This means that most of the weight of the brain is supported by the buoyancy force of the surrounding fluid. So here, in the figure, we have the number of balls that float in this device is measured as a measure of the density of the antifreeze solution in a vehicle's radiator, and consequently a measure of the temperature at which freezing will occur. The figure shows a common device that is used to check the antifreeze in a car radiator. The small balls in the enclosed tube vary in density so that all of them float when the tube is filled and with pure water. None float in pure antifreeze. One floats at 5% mixture, two at 10% mixture, and so forth. The number of balls that float in a measure of the percentage of the antifreeze in the mixture, which is in turn is used to determine the lowest temperature the mixture can withstand without freezing. So here's another example. So we have the orange balls in this plastic tube inside the battery serve as an indicator of whether the battery is charged, which is the case for the left, or discharged, which is the case on the right. The degree of charge in a car batteries can be determined when the so-called magic dot process that is built into the battery, as shown in the figure. Inside a viewing port in the top of the battery, the appearance of an orange dot indicates that the battery is sufficiently charged. A black dot indicates that the battery has lost its charge. If the battery has sufficient charge, the density of the battery fluid is high enough to cause the orange ball to float. If the battery loses its charge, the density of the density of the battery fluid decreases and the ball sinks beneath the surface of the fluid, making the dot appear black. So here's another question to consider. Atmospheric pressure varies from day to day. The level of a floating ship on a high pressure day is, the answer is no different than on a low pressure day. And the reason being that the level of floating of a ship is unaffected by the atmospheric pressure. The buoyancy force results from the pressure differential in the fluid. On a high pressure day, the pressure at all points in the water is higher than in a lower pressure day, because water is almost incomprehensible. However, the rate of change of pressure with depth is the same, resulting in no change in the buoyancy force. Here's another one. The density of lead is greater than that of iron, and both are denser than water. Compared to a solid iron object of the same dimensions, the buoyancy force acting on a solid object is, the answer is equal. Since both lead and iron are denser than water, both objects will be fully submerged, and since they have the same dimensions, will displace equal volume of water. Hence, the buoyancy force acts on the two objects will be equal. So here's a couple example here. On the left, we have seeing a streamline flow around an automobile and a test wind tunnel. The streamlines in the line flow are made visible by smoke particles. And on the right, we have hot gases made visible by smoke particles. The smoke first turns in laminar flow at the bottom and then into turbulent flow above. And so you can see that transition. Fluids in motions are streamline or laminar. If every particle that passes in a particular point moves along exactly the same smooth path followed by previous particles passing that point. This path is called streamline. As you can see in the figure on the left, different streamlines can cross each other under the steady flow condition, and the streamline at any point coincides with the direction of the velocity of the fluid at that point. Above a certain velocity or under any under any conditions that can cause an abrupt change in velocity, the flow of a fluid becomes irregular or turbulent. Irregular motion of the fluid cause eddy currents are characterized in turbulent flow, as shown in the figure on the right. We use the term viscosity to describe the degree of internal friction in the fluid. The internal friction is associated with the resistance between the two adjacent layers of the fluid moving relative to each other. A fluid such as kerosene has a lower viscosity than does crude oil or molasses. So many features of motion can be understood by considering the behavior of an ideal fluid. An ideal fluid satisfies these conditions listed here. So first, the fluid is non-viscous, which means that there is no internal friction force between adjacent layers. Number two, the fluid is incomprehensible, which means its density is constant. Number three, the fluid motion is steady, meaning that the velocity, density, and pressure at each point in the fluid doesn't change with time. And four, the fluid moves without turbulence. This implies that each element of the fluid has zero angular velocity above its center, so there can't be any eddy currents present in the moving fluid. A small wheel placed in the fluid would translate but not rotate. So in this figure, as we're exploring equations of continuity, a fluid moving with streamlined flow through a pipe of varying cross-sectional area, the volume of fluid flowing through A1 in a time interval delta t must equal the volume flowing through A2 at the same time interval. So the figure shown represents a fluid flowing through a pipe of non-uniform size, that the particles in the fluid moving along the streamlines in steady flow state. In a small time interval delta t, the fluid entering the bottom end of the pipe moves at a distance delta x1 equals v1 delta t, where v1 is the speed of the fluid at that location. If A1 is a cross-sectional area of the region, then the mass contained in the bottom blue region is given by the equation for delta M1, where nu1 is the density of the fluid at A1. In a similar way, the fluid that moves out of the upper end of the pipe in the same direction, same time interval delta t, has a mass given by the equation for delta M2. Because mass is conserved and because the flow is steady, the mass that flows into the bottom of the pipe through A1 in the time delta t must equal the mass that flows out through A2 in the same interval. So we can set the two expressions for mass equal, where delta t cancels out on both sides. For the case of incomprehensible fluid, nu1 equals nu2, and the result is called the equation for continuity. We see that the product of the cross-sectional area of the pipe and the fluid speed at the cross-sectional area is a constant. This means that the speed is higher when the tube is constricted and lower when the tube has a larger dimension. The product AV, which has dimensions of volume per unit time, is called the flow rate. The condition AV equals constant is equivalent to the fact that the volume of fluid entering one end of the tube in a given time interval equals the volume of fluid leaving the tube at the same interval, assuming that the fluid is incomprehensible and there are no leaks. So in this figure, we have water flowing slowly out of a faucet. And so the photo shows an example of an equation of continuity in action as the stream of water flows continuously from a faucet. The width of the stream narrows as it falls and speeds up. There are many instances in everyday experience that involve the equation of continuity, reducing the cross-sectional area of a garden hose by putting a thumb over the open end makes the water spray out with greater speed. That means that the stream goes farther. Similar reasoning explains why smoke from a smoldering piece of wood first rises in a streamline pattern, gets thinner with height, and eventually breaks up into a swirling turbulent pattern. The smoke rises because it's less dense than air, and the buoyancy factor of air accelerates it upward. As the speed of the smoke stream increases, the cross-sectional area of the stream decreases in accordance with the equation of continuity. The stream soon reached a speed so great that the streamline flow is not possible. So in this figure, by the work energy theorem, the work done by the opposing pressures P1 and P2 equals the difference in mechanical energy between that of the fluid, now between points C and D, and the fluid that was formerly between A and B. As the fluid moves through a pipe of varying cross-section and elevation, the pressure changes along the pipe. In 1738, the Swiss physicist Daniel Bernoulli derived an expression that relates the pressure of a fluid to the speed and elevation. Bernoulli's equation is a consequence of energy conservation as applied to an ideal fluid. We can derive this equation. We assume the fluid is incomprehensible, non-viscous, and flows in a non-turbulent, steady state manner. We can take a look at the figure. The fluid is flowing through this non-uniform pipe in the time delta t. The force on the lower end of the fluid is P1A1, where P1 is the pressure at the lower end. The work done on the lower end of the fluid by the fluid behind it is given by the equation for W1. Here, V is the volume of the lower blue region in the fluid. Similarly, we can find the work done on the fluid on the upper portion in the time delta t, W2. The work W2 is negative because the force on the fluid at the top is opposite its displacement. The equation of continuity tells us that the volume is the same. The net work is given by W fluid. Part of the work done, part of this work goes into changing the fluid's kinetic energy, and part goes into changing the gravitational potential energy of the fluid Earth system. If m is the mass of the fluid passing through the pipe in the time interval delta t, then we can write expressions for the change in the kinetic energy and the potential energy. Because the net work done by the fluid on the segment of the fluid shown in the figure changes the kinetic energy and the potential energy of the non-isolated system, we can equate the work done by the fluid to the change in the energy. So let's replace the three terms with our expression for each. Let's divide each term by V and use the definition of density to clean up the expression. The result is called Bernoulli's equation. Bernoulli's equation states that the sum of the pressure P, the kinetic energy per unit volume, 1/2 nu V squared, and the potential energy per unit volume, nu GY, has the same value at all points along the streamline. So in this figure, the device can be used to measure the speed of fluid flow. Venturi tube located at the top of the photograph, where we're seeing that the higher level of fluid in the middle column shows that the pressure at the bottom of the column, which is in the constricted region of the Venturi tube, is lower than the pressure elsewhere in the column. So let's look at this a little bit more and take a look at the figure, which shows water flowing through a horizontal constricted pipe from a region of larger cross-sectional area into a region of smaller cross-sectional area. This device is called a Venturi tube, can be used to measure the speed of the fluid flow. Because the pipe is horizontal, Y1 equals Y2, and Bernoulli's equation can be written as shown. Because the water is not backing up in the pipe, its speed V2 in the constricted area must be greater than its speed V1 in the region of the greater diameter. From our equation, we see that P2 must be less than P1 because V2 is greater than V1. This result is often expressed by the statement that swiftly moving fluids exert less pressure than do slowly moving fluids. The figure on the right illustrates this phenomenon. So let's think about this a little bit. So you observe two helium balloons floating next to each other at the ends of strings secured to a table. The facing surfaces of the balloons are separated by 1 to 2 centimeters. You blow through the opening between the balloons. What happens to the balloons? And the answer is they move toward each other. So the reasoning is when there is a moving airstream in the region between the balloons, the pressure in this region will be less than the opposite sides of the balloons where the air is not moving. The pressure differential will cause the balloons to move towards each other. This is a demonstration of the Bernoulli principle in action. So in this figure, we have a spinning golf ball is acted upon by lifting forces that allow it to travel much farther than it would if it were not spinning. In general, an object moving through a fluid is acting upon by a net upward force as a result of any effect that causes the fluid to change direction as it flows past the object. Take a look at the figure of the golf ball, for example. When the ball is struck with a club, it is given a rapid backspin. The dimples on the ball help entrain the air along the curve of the ball's surface. You can see a thin layer of air wrapping partway around the ball and being deflected downward as a result. Because the ball pushes the air down by Newton's third law, the air must push up and the ball and cause it to rise. Without the dimples, the air isn't as well entrained, so the golf balls doesn't travel as far. Tennis ball's fuzz performs a similar function, though the desired result is accurate placement rather than greater distance. So in this figure, we have a stream of air passing over a tube, dipped into a liquid, causing the liquid to rise in the tube. The effect is used in perfume bottles and paint sprayers. So let's look at the figure here, and the stream of air passing over the open tube reduces the pressure above the tube, causing the liquid to rise into the airstream. The liquid is then dispersed into a fine spray of droplets. You might recognize this so-called atomizer is used in perfume bottles and paint sprayers. The same principle is used in the carburetor of a gasoline engine. In that case, the low pressure region in the carburetor is produced by air drawn in by the piston through the air filter. The gasoline vaporizes, mixes with the air, and enters the cylinder of the engine for combustion. Here's an example for blood here. And so blood must travel faster than normal through a constricted region of an artery. In a person with advanced having trouble with blockage in their arteries, the Bernoulli effect produces a symptom called vascular flutter. In this condition, the artery is constricted as a result of accumulated plaque on its inner walls, as shown in the figure. To maintain a constant flow rate, the blood must travel faster than normal through the constriction. So here in the figure, the streamlined flow around an airplane wing. So the pressure above is less than the pressure below, and there is a dynamic upward lift force. So the lift on an aircraft wing can also be explained in part by the Bernoulli effect. The airplane wings are designed so that the airspeed above the wing is greater than the speed below. As a result, the air pressure above the wing is less than the pressure below, and there is a net upward force on the wing called the lift. There's also a horizontal component called the drag. Another factor influencing the lift on a wing shown in the figure is the slight upward tilt of the wing. This causes air molecules striking the bottom to be deflected downward, producing a reaction force upward by Newton's third law. Finally, turbulence also has an effect. If the wind is tilted too much, the flow of air across the upper surface becomes turbulent. The pressure difference across the wing is not as great as predicted by the Bernoulli effect. In an extreme case, the turbulence may cause the aircraft to stall. So we don't have the figure here, I apologize, but just think of an Apollo launch here, and I'll have to fix this. And so the exhaust speed of a rocket engine can also be understood qualitatively with Bernoulli's equations, although in actual practice, a large number of additional variables need to be taken into account. We can write the the exhaust speed is shown here from Bernoulli's equation, where P is the pressure inside the combustion changer, and the pressure just outside the nozzle is the atmospheric pressure, P sub atmospheric. The equation shown that the exhaust speed is reduced in the atmosphere, so rockets are actually more effective in the vacuum of space. Notice that the density in the denominator, a lower density working fluid or gas will give a higher exhaust speed, which partially explains why liquid hydrogen, which has a lower density, is a fuel of choice. So in this figure, that the net force on a molecule at A is 0 because such a molecule is completely surrounded by other molecules. The net force on a surface molecule at B is downward because it isn't completely surrounded by other molecules. If you get a chance to look closely at a dewdrop sparkling in the morning sunlight, you'll find that the drop is spherical. The drop takes the shape because of a property of liquid surface called surface tension. Let's see how surface tension works. Look at the figure. The sphere at A is a molecule in a container of water. Nearby molecules exert attractive forces on this molecule, but because it's completely surrounded by other molecules, the net force on it is 0. The molecule at B, on the other hand, is not attracted equally in all directions. Because there are no molecules above it to exert upward forces, the molecule at B is pulled towards the interior of the liquid. The contradiction at the surface of the liquid stops when the inward pull exerted on the surface molecule is balanced by the outward repulsive forces that arise from collisions with molecules in the interior of the liquid. The net effect of this pull on the surface molecules is to make the surface of the liquid contract and to make the surface area of the liquids as small as possible. Drops of water takes on a spherical shape because a sphere has the smallest surface area for a given volume. So in this figure, we see an end view of a needle resting on the surface of water. If you place a sewing needle very carefully on the surface of a bowl of water, you'll find that the needle floats, even though the density of steel is about 8 times that of water. The phenomena can also be explained by surface tension. The figure shows what is going on. The water surface acts like an elastic membrane under the tension. The weight of the needle produces a depression, increasing the surface area of the film. Molecular forces now act on all points along the depression, tending to restore the surface to its original horizontal position. The vertical components of these forces act to balance the force of gravity on the needle. The floating needle can be sunk by adding a little detergent to the water, which reduces the surface tension. So the surface tension is denoted by the Greek letter gamma. In a film of liquid is defined as the magnitude of the surface tension force divided by the length across which the force acts. The table shows a surface tension for a few materials. Surface tension can be thought of as the energy content of the fluids at the surface per unit surface area. To see this, let's manipulate units of the surface tension. In general, in any equilibrium configuration, of an object, the energy is a minimum. That means a fluid will take on shape such that its surface area is as small as possible. For a given volume, a spherical shape has the smallest surface area, which means that a drop of water takes on a spherical shape. So in this figure, we see an apparatus for measuring the surface tension of liquid. The force on the wire ring is measured just before the ring breaks free of the liquid. The figure shows an apparatus that's used to measuring surface tension of any particular liquid. A particular wire with a circumference L is lifted from a body of liquid. The surface film clings to the inside and outside edges of the wire, holding back the wire and causing the spring to stretch. If the spring is calibrated, the force required to overcome the surface tension of the liquid can be measured. In this case, the surface tension is given by the equation. We use 2L for the length because the surface film exerts the force on both the inside and the outside of the ring. The surface tension of the liquid decreases with increasing temperature because the faster moving molecules of a hot liquid aren't bound together as strong as those in a cooler liquid. Also, certain ingredients called surfactants decrease surface tension when added to liquid. For example, soap or detergent decreases the surface tension of water, making it easier for soapy water to penetrate the cracks and crevices of your clothes to clean them better than plain water does. A similar effect occurs in the lungs. The surface tissue of the air sacs in the lungs contain a fluid that has a surface tension of about 0.05 newtons per meter. A liquid with a surface tension that this high would make it very difficult for the lungs to expand during inhalation. However, as the area of the surface increases with inhalation, the body secretes into the tissue a substance that gradually reduces the surface tension of the liquid. At full expansion, the surface tension of the lungs fluid can drop as low as to 5 thousandths of a Newton meter. So here in the figure, we have a liquid is in contact with a solid surface on the top left. For water, the adhesive force is greater than the cohesive force. Then on the bottom for mercury, the adhesive force is less than the cohesive force. The surface of mercury curves downward in a glass container, while the surface of water curves upward as you move from the center to the edge. So this is something you may have noticed in the surface of liquid near the walls of a glass container curved upward as you move from the center to the edges, as shown in the top figure, say if you have a glass of water. But if you had mercury in a container, that it would be the opposite, which maybe is something you haven't seen. These surface effects can be explained by considering the forces between the molecules, and in particular the forces that the molecules of the liquid exert on one another, and the forces that the molecules of the glass surface exert on those of the liquid. The forces between like molecules, such as the forces between water molecules, are called cohesive forces, and the forces between unlike molecules, such as those exerted by a glass on the water, are called adhesive forces. Water tends to cling to the walls of the glass because the adhesive force between the molecules of water and the glass molecules are greater than the cohesive force between the water molecules. In effect, the water molecules cling to the surface of the glass rather than fall back into the bulk of the liquid. When this condition prevails, the liquid is said to wet the glass surface. The surface of the mercury curves downward near the walls of the container because the cohesive forces between the mercury atoms are greater than the adhesive forces between the mercury and the glass. A mercury atom near the surface is pulled more strongly towards other mercury atoms and towards the glass surface, so the mercury doesn't wet the glass surface. So in this figure, the contact angle between the water and paraffin is about 107 degrees. In this case, the cohesive force is greater than the adhesive force. And in another case here, when a chemical called a wetting agent is added to the water, it wets the paraffin surface, and phi is greater than 90 degrees. In this case, the adhesive force is greater than the cohesive force. So let's talk about this a little bit more. So if we look at the figure on here, the angle phi between the solid surface and a line drawn tangential to the liquid at the surface is called the contact angle. If the liquid has an adhesive force stronger than cohesive force, phi is less than 90 degrees and greater than 90 degrees for the opposite situation. So for example, if a drop of water is placed on a paraffin, the contact angle is approximately 107 degrees, as you can see in the figure on the left. If a certain chemical called the wetting agent or detergents are added to the water, the contact angle becomes less than 90 degrees, as seen in the figure on the right. The action of such substances to water ensures that the water makes thorough contact with the surface and penetrates it. For this reason, detergents are added to water to wash clothes or dishes. On the other hand, if sometimes necessary to keep water from making intimate contact with the surfaces, such as a waterproof clothing, waterproofing agent is used, which changes phi from less than 90 degrees to greater than 90 degrees. The water beads up on the surface and doesn't easily penetrate the clothes. So in this figure, we're looking at capillary action. So a liquid rising in a narrow tube because of capillary action or a result of surface tension and adhesion. The word capillary means hairline. In capillary tubes, the diameter of the opening is very small, on the order of 1/100 of a centimeter. And such a tube is inserted into liquid where the adhesive forces dominated over cohesive forces. The liquid rises into the tube, as you can see in the figure. The rising of the liquid in the tube can be explained in terms of the shape of the liquid surface and the surface tension effect. At the point of contact between the liquid and the solid, the upward force of surface tension is directed as shown in the figure. The expression gives the magnitude of the force. We use L equals 2 pi r here because the liquid is in contact with the surface of the tube at the points around its circumference. The vertical component of this force due to the surface tension is V sub F. For the liquid in the capillary tube to be in equilibrium, this upward force must be equal to the weight of the cylinder of water of height h inside the capillary tube. We can apply Newton's second law for equilibrium and equate V sub F to W. Solving for h gives the height to which the water is drawn into the tube. So in this figure, when cohesive forces between molecules of a liquid exceeds adhesive forces, the level of the liquid in the capillary tube is below the surface of the surrounding liquid. What about the case? In this figure, we want to be looking at the case when the cohesive forces dominate other adhesive forces in a liquid. The capillary tube is inserted in this type of liquid. The level of the liquid in the tube will be below the surface of the surrounding fluid as shown in the figure. Analysis similar to what we did with the previous slide would show that the distance h to the depression surface is given by the same equation. Capillary tubes are often used to draw small samples of blood from a needle, prick in the skin. Capillary actions must also be considered in the construction of concrete block buildings because water seepage through capillary pores in the blocks or the mortar may cause damage to the inside of the building. To prevent damage, the blocks are usually coated with a waterproofing agent, either outside or inside the building. Plants depend on capillary action to transport water and nutrients, and sponges and paper towels use capillary action to absorb spilled fluids. So here, as we look at viscous flow, in the figure, the particles are in an ideal that is non-viscous fluid are moving through the pipe with the same velocity. While on the other hand, in a viscous fluid, the velocity, the fluid particulars is zero at the surface of the pipe and increases to maximum value at the center of the pipe. Think about it pouring a glass of water out of a pitcher. Now imagine instead of you're pouring honey, it's much easier to pour the water. This is because honey has a higher viscosity than water. In a general sense, viscosity refers to the internal friction of a fluid. It's very difficult for layers of a viscous fluid to slide past one another. It's also difficult for one solid surface to slide past another if there is a highly viscous fluid between them. When an ideal or non-viscous fluid flows through a pipe, the fluid layer slide past one another with no resistance. The pipe has a uniform cross-section. Each layer has the same velocity as shown in the figure on the left. The figure on the right shows the layers of the viscous fluid have different velocities. The fluid has the greatest velocity at the center of the pipe, and the layer next to the wall doesn't move because of adhesive forces between the molecules in the surface layer. So in this figure, a layer of liquid between two solid surfaces in which the lower surface is fixed and the upper surface moves to the right with the velocity v. That's the case we're looking at. And so if we take a look at this figure, it shows a layer of liquid between the two solid surfaces. The lower surface is fixed in position. The top surface moves to the right with a velocity v under the action of external force F. Because of this motion, a portion of the liquid is distorted from its original shape, ABCD, to the shape AEFD at a moment later. The force requires to move the upper plane and distort the liquid is proportional to both the area A in contact with the fluid and the speed V of the fluid. Also, the force is inversely proportional to the distance between the two plates. Summing up these factors of force required to move the upper plate at a fixed speed at V is given by the equation shown, where eta is a coefficient of viscosity of the fluid. Sometimes the unit of viscosities are expressed in dynes per centimeter squared, called a poise, which is named in honor of the French scientist Poiseuille, who lived from 1799 to 1869. This relationship between the two units is shown. The coefficient of some viscosities are given in the table. So in this figure, the velocity profile of a fluid flowing through a uniform pipe of circular cross-section is shown. And the rate of flow is given by Poiseuille's law. The figure shown here is a section of a tube of length L with radius R containing a fluid under pressure P1 at the left and at a pressure P2 at the right. Because of the pressure difference of the fluid flows through the tube, the rate of flow or volume per unit time depends on the pressure difference, the dimension of the tube, and the viscosity of the fluid. The result is known as Poiseuille's law, where eta is a coefficient of viscosity in the fluid. We can notice that the rate of flow increases if the pressure difference across a tube or the tube radius increases. Also, the flow rate decreases if the viscosity of the fluid or the length of the tube increases. From Poiseuille's law, you can see that in order to maintain a constant flow rate, the pressure difference across a tube has to increase as the viscosity of the fluid increases. This fact is important in understanding the flow of blood through the circulatory system. The viscosity of blood increases as the number of red blood cells rises. Blood with a high concentration of red blood cells requires greater pumping pressure from the heart to keep it circulating than does blood of lower red blood cell concentration. Notice that the flow rates varies as the radius of the tube raised to the fourth power. This means that if a constriction occurs in a vein or artery, the heart will have to work considerably harder in order to produce a higher pressure drop and maintain the required flow rate. At sufficiently high velocities, fluid flow changes from simply streaming flow to turbulent flow, characterized by the highly irregular motion of the fluid. Experimentally, the onset of turbulence in a tube is determined by a dimensionless factor called Reynolds number, or Rn. It's given by the equation shown on the slide, where nu is the density of the fluid, v is the average speed of the fluid along the direction of the flow of the tube, and eta is the viscosity in the fluid. If Rn is above 2000, the flow of the fluid through a tube is streamlined. Turbulence occurs if Rn is above 3000 in the region, and in the region between 2000 and 3000, the flow is unstable, meaning that the fluid can move in streamlined flow, but any small disturbance will cause its movement to change to turbulent flow. So in this figure, we're talking about diffusion, and so we have a concentration of gas molecules on the left side out of a container exceeds the concentration on the right side. There will be a net motion that is diffusion of molecules from left to right. The basic mechanism for fluid flow through a tube is pressure difference across the ends of the tube. It's a difference that is responsible for the transport of a mass of fluid from one location to another. The fluid may move from one place from place to place because of a second mechanism, that it depends on the difference in the concentration between 2 points in the fluid as opposed to pressure differences. When the concentration, that is the number of molecules per unit volume, is higher at one location than another, the molecules will flow from the point where the concentration is high to the point where it is low. The two fundamental processes involved in fluid transport result from concentration differences, are called diffusion and osmosis. In a diffusion process, molecules move from a region where their concentration is high to a region where their concentration is low. To understand why diffusion occurs, let's look at the figure which shows a container with a high concentration of molecules introduced on the left-hand side. The dashed lines in the figure represents an imaginary barrier separating the two regions. Because the molecules are moving with high speeds in random directions, many of them will cross the imaginary barrier, moving from left to right. Very few molecules will pass moving from right to left simply because there are very few of them on the right side of the container at any instance. As a result, there will always be net movement from the region with many molecules to the region with fewer molecules. For this reason, the concentration on the left side of the container will decrease, and that on the right side will increase with time. Once a concentration equilibrium has been reached, there will be no net movement across the cross-sectional area. The rate of movement of molecules from left to right will equal the rate from right to left. This diffusion rate is a measure of the mass being transported per unit time. The basic equation for diffusion is Fick's law, where D is a constant of proportionality. The equation says that the rate of diffusion is proportional to the cross-sectional area A and to the change in concentration per unit distance, which is called the concentration gradient. The concentrations C1 and C2 are measured in kilograms per cubic meter. The proportionality constant D is called the diffusion coefficient and has units of square meters per second. And you can see in the table, it lists the diffusion coefficients for several substances. So in this figure, we're seeing an illustration of the human lung cells. Diffusion through cell membranes is vital. For example, in animals, diffusion carrying oxygen is to the cells of the body and removing carbon dioxide and other waste products from them. Cells require oxygen for those metabolic processes in which substances are either synthesized or broken down. In such processes, the cells use up oxygen and produce carbon dioxide as a byproduct. A fresh supply of oxygen diffuses from the cells where its concentration is high into the cell where its concentration is low. In the same way, carbon dioxide diffuses from the cell into the blood where it is a lower concentration. Water, ions, and other nutrients also pass into and out of the cell by diffusion. A cell can function properly only if it can transport nutrients and waste products rapidly across the cell membrane. The surface area of the cell should be large enough so that the exposed membrane area can exchange materials effectively, whereas the volume should be small enough so that the material can reach or leave particular locations rapidly. This requires a large area to volume ratio. So let's see if we can put some math into these criteria. And so if we were to model a cell as a cube, each side with length L, the total surface area is 6L squared, and the surface area to volume area is 6 over L. Because L is a denominator, a smaller L means a larger ratio. This shows that the smaller the size of a body, the more effective it can transport nutrients and waste products across the cell membrane. Cells range in size from a millionth of a meter to several millions. So a good estimate of a typical cell's surface to volume ratio is 10 to the 6. The diffusion of a material through a membrane is partially determined by the size of the pores or holes in the membrane's wall. Small molecules such as water may pass through the pores easily, while larger molecules such as sugar may pass through only with difficulty or not at all. A membrane that allows passage of some molecules but not others is called a selectively permeable membrane. So here in the figure, we're seeing red blood cells. Osmosis is the diffusion of water across a selective permeable membrane from high water concentration to low concentration. Imagine a particular cell in the body with sugar concentrations of 1%. A 1% solution of 1 gram of sugar dissolves in It dissolved in enough water to make 100 milliliters of solution. Let's assume the cell is immersed in a 5% sugar solution compared to a 1% solution. There are 5 times as many sugar molecules per unit volume in a 5% sugar solution. So there must be fewer water molecules. So water will diffuse from inside the cell where the concentration is higher across the cell membrane to the solution where the concentration of the water is lower. This loss of water from the cell would cause it to shrink and perhaps become damaged through dehydration. If the concentrations were reversed, water would diffuse into the cell, causing it to swell and perhaps burst. If solutions are introduced to the body intravenously, care must be taken to ensure that they do not disturb the osmotic balance of its cells or damage can occur. For example, if a 9% saline solution surrounds a red blood cell, the cell will shrink, but if it is surrounded by 1%, the cell will eventually burst. So in this figure, we're seeing a diagram of a single nephron in the human excretory system. And in the other one, we're seeing an artificial kidney. So let's take a look at the figure on the left. In the body, blood is cleansed of its impurities by osmosis as it flows through the kidneys. Our arterial blood first passes through a bundle of capillaries known as glomerulosus, where most of the waste products are some essential salts and minerals are removed. From the glomerulosus, a narrow tube emerges that is in intimate contact with the other capillaries throughout its length. As blood passes through the tubules, most of the essential elements are returned to it, waste products are not. To re-enter, are not allowed to re-enter and are eventually removed in urine. If the kidneys fails, an artificial kidney or dialysis machine can filter the blood. The figure on the right shows how this is done. Blood from an artery in the arm is mixed with hairpin, a blood thinner, and allows it to pass through a tube covered with a semi-permeable membrane. The tubing is immersed in a bath of dialysis salt, fluid with the same chemical composition as purified blood. Waste products from the blood enter the dialysis by diffusion through the membrane. The filtered blood is then returned in a vein. So in this figure, we have a sphere falling through a viscous medium. The forces acting on the sphere are the resistive frictional forces V, F sub R, the buoyant forces B, and the forces of gravity W acting on the sphere. When an object falls through air, its motion is impeded by the force of air resistance. In general, this force depends on the shape of the falling object and on its velocity. The force of air resistance acts on the same falling object, but the exact details of the motion can be calculated only for a few cases in which the object has a simple shape, such as a sphere. Let's examine the motion of a tiny spherical object falling slowly through a viscous medium as shown in the figure. In 1845, a scientist named George Stokes found that the magnitude of the resistive force on a very small sphere object of radius r falling slowly through a fluid of viscous eta with speed v is given by the equation here. It's named the Stokes law in his honor. So take a look at the figure as a sphere falls through a viscous medium. 3 forces act on it: V sub r, then the force of friction, B, and B, the buoyant force of the fluid, and W, the force of gravity acting on the sphere. Here's the magnitude of W, where nu is the density of the sphere, and 4/3 pi r cubed is the volume, and of the volume buoyance force equals to the weight of the fluid displaced by the sphere, where nu f is the density of the fluid. At the instance the sphere begins to fall, the force of the friction is 0 because the speed of the sphere is 0. As the sphere accelerates, the speed increases, and so does f sub r. Finally, at the speed called the terminal speed, B sub t, the net force goes to zero. This occurs when the net upward forces balances the downward force of gravity. Let's find an expression for the terminal speed. First, equate the sums of the friction and buoyant forces to the weight and substitute the expression. The result is the equation for terminal velocity. If an object isn't spherical, we can still use the basic approach described in the previous slide to determine its terminal speed. The only difference is that we can use Stokes' law for the resistance force. Instead, we'll assume that the resistance force has a magnitude proportional to its velocity, where k is a coefficient of proportionality, which will need to be determined experimentally. We know the object reaches its terminal speed when the downward force of gravity is balanced by the net upward force. The volume V of the displaced fluid is related to the density nu of the falling object, so we can express the buoyant force in terms of densities. Substituting our expressions into the terminal speed relationships, we get the result. So here we have a simplified diagram of a centrifuge. The terminal speed for particles in biological samples is usually quite small. For example, the terminal speed for blood cells falling through plasma is about 5 centimeters per hour. In the gravitational field of the Earth, the terminal speeds for the molecules that make up cells are many orders of magnitude smaller than this because of their smaller mass. The speed at which materials fall through a fluid is called the sedimentation rate and is important in clinical analysis. The sedimentation rate in a fluid can be increased by increasing the effective acceleration g that appears in our equation for terminal velocity. In the figure, a fluid containing various biological molecules is placed in a centrifuge and whirled at very high angular speeds. Under these conditions, the particles gain a large radial acceleration that is much greater than the free fall acceleration, so we can replace g in our equation with the angular acceleration. Similarly, we get this result. The equation shows us that the sedimentation rate is enormously speed up by a centrifuge because the angular acceleration is much greater than the acceleration, the gravitational acceleration, and those particles with the greatest mass will have the largest terminal speed. That means that the most massive particles will settle out at the bottom of the test tube first. You might think that a solid has a rigid shape and volume, but it's possible to change its shape and volume by applying external forces. A sufficiently large force will permanently deform or break up objects, but otherwise, when the external forces are removed, the object tends to return to its original shape and size. This is called elastic behavior. The elastic properties of solids are discussed in terms of stresses and strains. Stress is the force per unit area causing a deformation. Strain is a measure of the amount of the deformation for sufficiently small stresses. Stress is proportional to strain, with a constant of proportionality depending on the material being deformed and on the nature of the deformation. We call this proportionality constant the elastic modulus. The elastic modulus is analogous to spring constant. You can think of it as a stiffness of the material. The material having a large elastic modulus is very stiff and difficult to deform. There are three relationships having the form of the equation shown, corresponding to tensile shear and bulk deformation, and all of them satisfy equations similar to Hooke's law for springs, where F is the applied force, K is the spring constant, and delta X is essentially the amount at which a spring is stretched or compressed. So in here we have an illustration of a force that's applied to a long bar clamped at one end. So the figure shows a long bar of cross-sectional area A and length L sub O clamped at one end, where an external force F is applied along the bar perpendicular to the cross-section. Internal forces in the bar resistance the distortion or stretching that F tends to produce. The bar attains an equilibrium where its length is greater than L sub 0, and the external force is balanced by internal forces. In this situation, we say that the bar is stretched. The tensile strength is a ratio of the magnitude of the external forces F to the cross-sectional area A. The word tensile has the same root as the word tension and is used because the bar is under tension. The tensile strain is defined as the ratio of the change in length delta L to the original length L, and is therefore a dimensionless quantity. We can write an equation relating tensile strength to tensile strain, where Y is a constant of proportionality called Young's modulus. The SI units of stress is newtons per meter squared, called the Pascal, which is the same unit as pressure. Let's solve the equation to make it look like Hooke's law, where K is equal to YA divided by L0. So the table shows some typical values for the Young's modulus. A material having a large Young's modulus is difficult to stretch or compress. The quantity is typically used to characterize a rod or a wire stressed under either tension or compression. Experiments show that the change in length for a fixed external force is proportional to the original length, and the force necessary to produce a given strain is proportional to the cross-sectional area. The value of Young's modulus for a given material depends on whether the material is stretched or compressed. A human femur, for example, is stronger under compression than tension. Here in the figure, we have us looking at the stress versus strain curve for an elastic solid. It's possible to exceed the elastic limit of a substance by applying a sufficiency great stress, as you can see in the graph. At the elastic limit, the stress strain curve is no longer a straight line. A material substance subjected to a stress beyond this limit ordinarily doesn't return to its original length when the external force is removed. As the stress has increased further, it surpasses the ultimate strength, the greatest stress the substance can withstand without breaking. The breaking point for brittle materials is just beyond the ultimate strength. For a ductile metal like copper and gold, after passing the point of ultimate strength, the metal thins and stretches at a lower stress level before breaking. Okay, in the figure, we have a shear deformation in which a rectangular block is distorted by forces applied tangent to the two of the faces. And in the other figure, we see a book under shear stress. So another type of deformation occurs when an object is subjected to a force P parallel to one of the faces, while the opposite face is held fixed by a second force, as you can see in the figure on the left. If the object is originally a rectangular block, parallel force results in a shape with the cross section of a parallelogram. This kind of stress is called a shear stress. The book in the figure on the right is being pushed sideways and is subject to a shear stress. There's no change in the volume with this kind of deformation. Remember that in shear stress, the applied force is parallel to the cross-sectional area, and the tensile strength, the force is perpendicular to the cross-sectional area. We define the shear stress as F over A, the ratio of the magnitude of the parallel force to the area A of the face being sheared. The shear strain is the ratio of delta X over H, where delta X is the horizontal distance and the shearing face moves, and H is the height of the object. The shear stress is related to the shear strain according to the equation shown, where S is the shear modulus of the material, where units of Pascal. Notice the similarity to Hooke's law. A material having a larger shear stress is difficult to bend. Shear modulus for some materials are listed in the table. Okay, in this figure, we have a solid cube is under uniform pressure and is therefore compressed on all sides by forces normal to its 6 faces. The arrowheads for force vectors on the sides of the cube that are not visible are hidden by the cube. The bulk modulus characterizes the response of a substance to a uniform squeezing. Imagine that an external force acting on an object are all perpendicular to the surface on which the forces act and are distributed uniformly over the surfaces of the object as shown in the figure. This occurs when an object is immersed in a fluid. An object subject to this type of deformation undergoes a change in volume, but no change in shape. The volume stress delta P is defined as a ratio of the change in the magnitude of the applied force delta F to the surface area A. From the definition of pressure, delta P is also simply a change in pressure. The volume strain is equal to the change in volume delta V divided by the original volume V. We can relate a volume stress to a volume strain by the formula shown. Material having a large bulk modulus doesn't compress easily. Note that a negative sign is included in this defining equation so that B is always positive. An increase in pressure, positive delta P, causes a decrease in volume, negative P, and vice versa. The table lists bulk modulus values for some materials. If you look up such values in a different source, you may find that the reciprocal of the bulk modulus called the compressibility of the material is listed. Note that from the table that both solids and liquids have bulk moduli. There is neither a Young's modulus nor Shear's modulus for liquid. However, because liquids simply flow when subject to a tensile or shear stress. The ultimate strength of material is the maximum force per unit area the material can withstand before it breaks or fractures. These values are very important in the construction of buildings, bridges, and roads. The table shows the ultimate tensile and compressive strength for different materials. Note that some substances like bones are stronger under compression than tension. So in this figure, we have a simple post and beam structure. In ancient times, a principal method of spanning a space was a simple post and beam construction shown in the figure, where a horizontal beam is supported by two columns. This type of construction was used to build the Greek temples. The columns of these temples were closed spaces because of the limited length of available stones and the lower ultimate tensile strength of the sagging stone beam. So here's a semicircular arc developed by the Romans, and the greater ability of bricks and stones to resist compression in the basis of a semicircular arc is shown in the figure. The architectural style was developed by the Romans. It was a great technological achievement. It effectively allowed the heavy load of a wide roof span to be channeled into a horizontal and vertical forces as narrow supported columns. The stability of the arch depended on the compression ability between its wedge-shaped stones. The stones are forced to squeeze against each other by the uniform loading as shown in the figure. This compression results in horizontal outward force at the base of the arch, where it starts curving away from the vertical. These forces must then be balanced by the stone walls shown on the sides of the arc. It's very common to use very heavy walls called buttresses on either side of the arch to provide horizontal stability. If the foundation of the arch should move, the arch might collapse. The stone surfaces used in the Roman arches were cut to make very tight joints. Mortar was usually not used. The resistance to slipping between the stones was provided by the compression force and the friction between the stone faces. So here we see the Gothic arch with flying buttresses to provide lateral strength, lateral support. Another important architectural innovation was the pointed Gothic arch shown in the figure. This type of structure was used in Europe beginning in the 12th century, followed by the construction of the several magnificent Gothic cathedrals in France in the 13th century. It forms one of the most striking features of these cathedrals is their extreme height. For example, the cathedral at Cartes rises to 118 feet, and the one at Reims was a height of 137 feet. Such magnificent buildings have evolved over a very short period of time without the benefit of any mathematical theory or structures. However, Gothic arches require the flying buttresses to prevent the spreading of the arch support by tall, narrow columns. So we'll just take a few minutes. I'm just going to breeze through these in terms of assessing to learn. So the first one we have here, the answer is a scale A reads the same as scale B. For this one, scale A reads the same as scale B. For this one, block B has a larger buoyant force on it. And for this, the level decreases. The answer to this one, the volume decreases. And the answer for this, the level stays the same. So we've covered an incredible amount of material here. It's been a little bit longer than I would like. In terms of a summary here, states of matter, the matter is normally classified as being one of three states: solid, liquid, or gaseous. The fourth state of matter is called plasma, which consists of a neutral system of charged particles interacting electromagnetically. For density and pressure, the density nu of a substance of uniform composition is the mass per unit volume, kilogram per cubic meter in the SI units. The pressure P is the fluid measured in pascals, is a force per unit area that fluid exerts on an object immersed in it. Variations of pressure and depth. The pressure in an incomprehensible fluid varies with the depth h according to the expression shown, where P sub 0 is atmospheric pressure and nu is the density of the fluid. Pascal's principle states that when pressure is applied to an enclosed fluid, the pressure is transmitted under undiminished to every point of the fluid and to the walls of the containing vessel. And just finishing up here, last chart, buoyant forces and Archimedes principles. When an object is partially or fully submerged in a fluid, the fluid exerts an upward force called the buoyant forces on the object. This force is in fact due to the net difference in pressure between top and bottom of the object. It can be shown that the magnitude of the buoyant force B is equal to the weight of the fluid displaced by the object. The equation is known as Archimedes' principle. Solving a buoyancy problem usually involves putting the buoyant forces into Newton's second law and then proceeding as in topic 4. For fluids in motion, certain aspects of a fluid in motion can be understood by assuming the fluid is non-viscous and incomprehensible, and that its motion is in a steady state with no turbulence. So number one, the flow rate through the pipe is constant, which is equivalent to stating that the product of the cross-sectional area A and the speed V at any point is constant. And any 2 points, therefore, we have the first relationship shown on the slide. The relationship is referred to this equation of continuity. Number two, the sum of the pressure, the kinetic energy per volume, and the potential energy per volume is the same at the 2 points along a streamline. The equation is known as Bernoulli's equation. Solving problems with Bernoulli's equation is similar to solving problems with the work energy theorem, where 2 points are chosen, 1 point where a quantity is known and another where all quantities are known. Bernoulli's equation is then solved for the unknown quantity. For the deformation of solids, the elastic properties of solids can be described using the concepts of stress and strain. Stress is related to the force per unit area producing a deformation. Strain is a measure of the amount of deformation. Stress is proportional to strain, and the constant of proportionality is the elastic modulus. There are three types of deformation. The first is the resistance of a solid to elongation or compression is characterized by Young's modulus Y. Second, the resistance to displacement of the faces of a solid sliding past each other is characterized by the shear modulus S. And three, the resistance of a solid or liquid to a change in volume characterized by the bulk modulus B. All three types of deformations obey laws similar to Hooke's law for springs. Solving problems is usually a matter of identifying the given physical variables and solving for the unknown variables. Okay, well, thank you very much. Sorry for a long lecture, but there was a lot of material. Take care.